As the question says, a hydrogen atom in a state having a binding energy of 0.85 electron volts makes transition to a state with excitation energy 10.2 electron volts. Identify the quantum number n of the upper and the lower energy states involved in the transition, and B, find the wavelength of the emitted radiation. Now they are saying the binding energy of that is 0.85 electron volts, and for hydrogen we know 1, 2, 3, 4, that for fourth one it is 0.85 electron volts, the energy, or you can say the binding energy. Initially we have 13.6, I'm writing just the magnitudes, then 3.4, right? So I'm not writing the energy of third because we don't need that in this part. So what here is that the binding energy is 0.85, which means that the n is equals to 4 over here, because by this data. Now this makes transition to a state with excitation energy 10.2. This means that it is actually going to an energy state N1 for which the excitation energy is 10.2. And what is excitation energy? It is the energy needed to go from the ground state to that value of N. Now that energy is 10.2, and that you can see is from 1 to 2, because when you move from n equal to 1 to 2, you need a photon of 10.2 electron volts. So we can say that this N1 is basically coming out to be 2. So the actual transition is from 4 to 2, and this is actually the first part of this question. Now the second part is to find the wavelength of the emitted radiation. Now since the transition is from 4 to 2, we can easily find out the wavelength, which is simply 1 by lambda equals to r z square into 1 by n1 square. Now n1 is where the electron is actually coming, and this is basically having this makes transition to a state n equal to 2 minus 1 by 16, that is n2 square. So this being n1 and this being n2. Now keep it in mind, because this is n2 and this is n1, because this actually comes out to be positive, because lambda cannot be negative. So lambda equals to 487 nanometers.